shining a light to the eyes, like flickering a light at 40 hertz or strobing sound at 40 hertz. By doing that, it can help improve biometrics that are associated with Alzheimer's disease, as well as improve cognitive functions such as long-term memory function.
Welcome to the Evolving Past Alzheimer's podcast, where we are focused on bringing you information to help prevent from developing and improve from suffering with brain diseases like Alzheimer's and other dementias. I'm Dr. Nate Bergman, a physician and Chief Scientific Wellness Officer at Kemper Cognitive Wellness, and I'll be your guide on these sound waves. So whether you're a baby boomer who's worried that your brain wiring just isn't working like it once was, or you have a loved one with the disease, or you yourself have already been diagnosed and are wondering, what do I do now? You'll want to listen to this podcast. Each episode, we introduce you to the top doers and thinkers that are revisioning Alzheimer's, dementia, and just generally things in life's second half. If you have questions or comments, check us out on social media. To support us, go to patreon.com/evolvingpast and consider hitting the button and becoming a patron of this show if you find these episodes valuable. That's Patreon, Patreon, patreon.com/evolvingpast. So here we go. Let's get better. Welcome back to the show. I'm super excited and thrilled to have our guest this week, Dr. Theodore Ted Zanto. He's an associate professor in neurology at the University of California, San Francisco, and the director of the Neuroscience division. Dr. Zanto utilizes brain imaging, usually fMRI and EEG, and non-invasive brain stimulation techniques to study essentially how the brain works. He's particularly interested in the intersection of attention, perception, and memory. Now, I know that sounds like a mouthful, but I promise you that it's interesting. This may get a little technical. People can refer back to some of our episodes with Dr. Adam Woods and Dr. Ben Hampstead in the past that are sort of maybe similar flavor. Certainly, if you have questions, you can write in. But Ted, you and I met at a wonderful little virtual conference out of Toronto a couple months ago. I was fascinated by both the content, both of your talks. And then we had like these kind of fun virtual hallway discussions. So welcome to the show. Thanks for being here.
Thanks for having me, and definitely fun conversations that we've had in the past. So I'm looking forward to keeping it going.
I know that you didn't start off as an Alzheimer's researcher, but can you kind of frame for people where you're at in your career right now, especially as it kind of angles towards the Alzheimer's piece?
Yeah, so I got into neuroscience research long ago because of my interests in, as you said, attention, perception, memory. These three things work together harmoniously. You're not going to remember something that you don't pay attention to, and it's hard to pay attention to something if you don't perceive it in the beginning. So obviously, these things work intuitively together. And how the brain enables that has been a mystery for much of my life. Over the years, though, we've learned a lot along the way, and I like to think that I've contributed a little bit to that field of research. And so I went to graduate school actually to study how the brain encodes the beat to music. And so I was using that really as music perception as a window into how that enables us to pay attention, to listen, and hopefully to remember information. And after I graduated, I went to California, University of California in San Francisco, and worked with Adam Gaza, and we did a lot of great research on attention and memory and perception in aging. And again, this is just a really fascinating field for me to understand not just how the brain enables us to pay attention and remember things, but then how does that process change as we get older? And what really shocked me was the fact that as we get older, many older adults will go to their doctor and complain of memory issues. And their doctor will say, well, that's kind of just normal healthy aging. Just like that seems like an unacceptable answer. Just is very, very frustrating. And
hey, doc, my knee hurts. You're just getting older, right? We have more sophisticated answers when his knee hurts, right?
Yeah, that's salt in the wound, insult to injury. It just feels very unsatisfactory of an answer. And some of our research, as well as others, have at least indicated that some of these memory issues stem from attentional issues, specifically inhibiting irrelevant information.
So people can't filter things out appropriately?
Yeah. If you think about it, you're bombarded with a myriad of pieces of information. Generally, you're not paying attention to the chair you're sitting on or the lights around you, maybe the desk in front of you, or all these little bits of sensory stimuli that you're really not focusing on. But if you lose the ability to filter out distraction, it's going to be very hard to carry on a conversation, say, in a noisy environment where you're, say, in a restaurant and people are speaking all around you, and you need to filter out those distractions and focus on the content that's at hand. So apparently, as we and others have seen, as we get older, some of this filtering degrades, and that results in memory issues. Now, to be fair, what's interesting is that although in a lab we can test, younger and older adults on memory performance, and then as we add in distraction, the older adults, healthy, remember, quote unquote, healthy older adults will show deficient memory performance compared to younger adults. But that's when you test them on the content that we told them to remember. If you test them on the content that they were supposed to ignore, older adults are actually remembering that better. So it's not that they're really having a problem with memory capacity. It's just an attentional filtering issue. Now, of course, this is just one example of many other issues that could arise as to why memory might degrade as we get older. But, I just found that really, really fascinating. And as I got, further and further into aging research, I spent less and less time just understanding the basic fundamentals of how the brain works and just, more or less focused on what goes wrong and how can we fix it. And so then a lot of my attention, my research energies went into assessing different potential therapeutics that might help people focus their attention and hopefully improve their memory performance. So yeah, to do this, I've been studying largely two branches of interventions. One revolves around music and musical training as a means to facilitate attention and memory performance, and the other revolves around non-invasive neurostimulation using magnetic fields or electrical currents to entrain neural oscillations, meaning entrain frequencies of the brain that underlie attention and memory processes, and try to sort of rescue or enhance some of those cognitive abilities in order to sort of remediate age-related declines.
So I'm very fascinated, but I want to make sure, I want to bubble back out and say, just what do you mean by perception with as much precision as you can? Like you mentioned, the nexus or the connection between attention, memory, and perception. What aspect of perception is it that you've been focusing on or you found important? Like, what do you mean by that?
Yeah. So when I speak of perception, I'm really just talking about it at a fairly high level, not really at the systems neuroscience level of the individual neurons and such, but I'm really more focused on perceiving or experiencing sensory stimuli, such as the sound of my voice or a picture, and so I'm focused mostly on vision and audition. So your ability to see, your ability to hear. And what's important is that in the brain, you have sensory specific regions. So there is a region of the brain dedicated to visual processing. And there's another region of the brain dedicated to auditory processing. And of course, these regions are highly connected to other regions of the brain. And as I had mentioned earlier, attention will help bias your perception, right? So sort of filter out distraction. And the way it does that is by ramping up the gain or making brain regions or large groups of neurons more sensitive to the stimuli that you're trying to detect. So if you're trying to pick out the words that you're saying, that you specifically are saying to me amongst a noisy crowd, I know what your voice sounds like, so I can sort of tune my auditory cortex. I can tune it to sort of ramp up the sound of your voice so that it sort of comes through better than all the distracting noises around me. That's, sort of a hand explanation.
Sort of like an old transistor radio for people who remember the sort of digital time, Okay, even digital to some extent.
Or really, it's kind of like an equalizer. Let's move the mids up and lower the bass and lower down the treble and bring up, just your voice and block out the highs and the lows.
Of tuning in. Okay, and then just if you could just say a little bit just on, even though we've had several episodes on this, just assuming somebody's never kind of heard of a neural oscillation or maybe like a brainwave or something like that. Why are those important? Like, why do we think there's kind of information that is useful in those?
Yeah. So why are we interested in brain oscillations? Well, brain oscillations just means the frequencies at which the brain or the neurons within your brain are firing, right? So they become active at different frequencies. So when you're sleeping, you get these really slow bursts of activity. between 1 and 4 hertz generally. And we would call these sort of delta waves, these really low frequency, slow waves. And, for those who are unfamiliar with what a hertz is, 1 hertz would mean 1 cycle per second, or essentially like 1 burst of activity every second.
If you're doing a lap around a track, it would be 1 lap in a second. Okay.
Yeah, exactly. And if you're doing 4 hertz, that'd be like 4 laps around the track.
And how fast do we know the brain can go? Like up to what?
Well, that's a bit of a debate. Any single neuron can briefly burst, kind of like the human can only sprint max out for a very short amount of time. From my understanding, you can get neurons to burst, in the kilohertz range, like around 1,000 hertz. But for very short amounts of time, generally, they're oscillating at lower frequencies because other neurons will pick up the slack. And so if you were to record large groups of neurons, then you can get higher and higher frequencies. And, you can sort of pick out what we would consider neural codes from that. But how the brain does this, any individual neuron is not going to fire more than, in the low kilohertz, like 1 kilohertz or so. But you can get groups of neurons that are communicating, and then you can sort of detect the group to be oscillating at a much higher frequency. But no one neuron is firing at 10,000 hertz or something. You know what I mean?
And so when you are studying this, you're looking at groups and you're looking at networks. You're not looking at one at a time.
Right. So that's why I was saying I'm not really at the systems level, at the individual neuron level, but I use tools like EEG, electroencephalography, or fMRI, functional magnetic resonance imaging. And these are looking at, large swaths of cortex, which would include tens, hundreds of thousands of maybe millions of neurons in one group. And when you get to that number of neurons all synchronously firing together, so with EEG, it has really fine temporal resolution. And so you can detect sort of these oscillations. With EEG, you're maxing out probably around, 60, 70 hertz, right? So you're certainly not getting the resolution that you would need to get an individual neuron, but you can gain a lot of really interesting information from 70 hertz and below. And I was saying, different cognitive states are associated with different frequency bands, meaning like, as I was saying, delta, this low frequency 1 to 4 hertz seems to be pretty dominant when you're asleep. And in waking life, you have these other, frequency bands that are associated with, attention and memory and perception, things like that. And so
super interesting. I want to actually kind of modify as you're talking. I'm thinking, okay, well, how to make your work and some of the things that might seem esoteric over a couple of decade-long career, right? We're never, obviously, in the time that we have, we can't talk about everything that and everything, but like in all of the observations, but like in some sense, starting with the end in mind, because, obviously my understanding of the goal of Neuroscape where you work at UCSF and like, your own personal goals, that it's just, okay, how do we impact humanity for the greater good? How do we and specifically here, how do we help people's brains and cognitive process improve? And you've worked with, virtual reality and music and beats and various kinds of stimulations with, measuring other kinds of interesting things. And maybe we'll talk about at the end, like some new things, maybe there's some of this sort of psychedelics that you might be having access to because of new personnel over there at UCSF and Neuroscape. Like from what you know right now, or what you think, and this, I realized that this is some conjecture, but if you could sort of say, hey, if I could do anything I wanted with a group of people that have sort of a little bit broken brains, they're sort of limping along, right? Whether it's the person who's having trouble finding words, or they're really forgetting stuff, or they're maybe just at the very beginnings of a Alzheimer's or sort of a mild cognitive impairment. And you could say, hey, from the perspective of the things and the tools that you've been involved with, music, stimulation, etc., even virtual reality, let's say, what would it probably look like? What would that intervention or that program what would it look like?
Yeah, our day-to-day research usually revolves around research questions. And so we don't just leave our doors open and whoever has a problem just sort of stumbles in and say, oh yeah, I was just in a car crash. I just suffered traumatic brain injury and I need an intervention to deal with this. Rather it's sort of the other way around. We develop interventions in line with the cognitive functions that we've already been studying. So as I said, my work is coming from assessing how attention, memory, and perception sort of interact with each other across the lifespan, how it degrades potentially as we get older, and then how we might remediate that. And so in the course of studying just how the brain works, we've identified specific mechanisms that we believe would be great targets for specific interventions. So, for example, some colleagues of mine, Joaquin Anguera and Adam Gaza, ran a really interesting study assessing multitasking abilities.
So the ability to do a few things sort of at the same time, pay attention and move forward a couple of things at the same time.
Yeah, actually, in order to assess multitasking, they had people across the lifespan, well, adult lifespan, I think it was 18 to 80 was their range that they were studying. And they had all these people come into the lab and play a video game. It was essentially a little car simulation. They're driving a car and they just have to respond to street signs, right? This is if you have a driver's license, this is a very common thing to do.
That's the NeuroRacer program? NeuroRacer?
Yeah, NeuroRacer. Yeah, so they did this experiment and it was really to assess, multitasking abilities. And they saw that, the ability to multitask, to drive a car and respond to street signs simultaneously was related to this frontal theta oscillation, meaning in the frontal part of the brain, there was this burst of activity that was around 6 hertz, 6 pulses of brain activity.
Slower, but not the slowest.
Yeah, exactly. It's still pretty slow, but it's not the slowest. And
so this group had more of that sort of theta, more of that sort of somewhat slow. Okay.
Yeah, so like the best performers, really, they were the younger adults. Go figure that they're more likely to be gamers also, but nonetheless, what they see is that, the ability to multitask sort of peaks in the 20s and then it just sort of goes, slowly downhill from there. And the brain activity kind of followed that, where you have sort of a really large frontal theta activity in the younger adults and less so as you get older. However, with practice, or what you'd call training, cognitive training, just keep playing this over and over again. Adam and Joaquin Anguera and them, they randomly assigned a subgroup of these older adults to training. And just after a month of playing this multitasking paradigm of basically driving a car and responding to street signs, they're able to improve multitasking abilities and improve this frontal theta activity. So there really did seem to be a link there that, this frontal theta activity seems to be involved in this complex cognitive function, your ability to multitask, drive and respond to street signs simultaneously. And it was also related to other tasks that were not even driving with street signs. They show that frontal theta was also related to your ability to focus your attention and remember objects. And so it was interesting that this training helped other cognitive abilities that weren't related to the trained task. So that was pretty exciting. And so one of my questions is, it took a month to get there. Is there any way we could make this a little more efficient? What would happen if we were to actually apply a stimulus, apply an oscillating current with electricity?
So play the game and stimulate your brain while you're playing the game. Okay.
Yeah, exactly. So we did this study in healthy young adults. And we said, let's see if we can boost their performance. I mean, they're already sort of at the peak of the game, but let's just see if we can facilitate their abilities by just stimulating at this 6 hertz theta region. And sure enough, within an hour of stimulation, those that were stimulated at 6 hertz or what we call, theta stimulation were the ones that showed the greatest improvements in multitasking ability just after an hour compared to a group that received, like a control stimulation where they could feel the stimulation, but they weren't actually getting like the full dose. And so that was really exciting. And then we replicated it because we weren't sure if we could believe it. And so we were able to replicate it. And then we did it again, replicated it another time in older adults, because that was really in the end what we were trying to target. But we wanted to make sure it actually worked, first of all, because it's a lot easier to recruit younger adults than it is older adults. So we were like, let's just do it a bunch of times in younger adults.
See if it's real and know what's right. Okay, that's good. All right, I get it. So a good strategy there.
Yeah, exactly. So that's kind of how we go about our research. Is we usually base something off of a finding. We say, oh, you know what? This is a potential target. Maybe we can develop an intervention around it.
Okay. And then let me ask you another, probably this would be a theoretical question, although maybe not. So let's say you have the game and you have the stimulation. What about adding music, which you have quite a bit of experience with, or some kind of musical entrainment to that as well? This sort of multiple things approach.
Yeah, I love that idea. Maybe I wasn't clear about this. When they're receiving the stimulation, they're engaged in the multitasking paradigm, right? So we know that this game, this driving the car and responding to street signs, we know that will elicit theta activity. And so when we apply theta stimulation, what we're really trying to do is sort of entrain the ongoing neural activity. So if we were to play music, that might evoke different brain activity than what we're really targeting. So we have to do it very carefully in how we do this.
So let me make sure everybody's tracking with me and make sure I'm tracking with you. So when you're doing stimulation, so you're literally putting like electrodes on someone's head and you're feeding the brain the frequency, right? You mentioned this, how many laps are on the track in a second, so to speak. The 7 laps are on the track in a second, 7 hertz frequency, something like that, 6, 7 hertz frequency to people. And where are you putting those electrodes on the head?
Yeah, so these electrodes, they're about the size of a nickel or a quarter, and they go right sort of, if you were to go basically straight above your eyes, the top of your skull, and then sort of over just a little bit, a little more lateral.
What we may call F5, F6, or F3,
F4. F4, if you're familiar with EEG electrode coordinates.
So sort of, I call that where like the sort of men usually get, the receding hairline area, sort of the typical receding hairline area for most men.
Yeah, just behind the receding hairline. Yeah, it'd be just behind there. If you're familiar with brain anatomy, it's generally above dorsolateral prefrontal cortex. But yeah, if you're just looking at someone's head, yeah, you're right. I think the hairline's a pretty good marker, but behind the hairline. So we have to apply a little bit of gel because, the electrodes aren't going to touch the scalp unless you shave their head. But for some reason, participants don't want us shaving their heads. So
yeah. Now, these kinds of things. So how long did you follow the people that had these improvements? Did you follow them up after, not just after a session, but like a month after the session? Like how long did the results last for?
Yeah, great question. That was definitely, once we demonstrated efficacy in younger adults, that was one of our key questions when we moved this over to older adults. Because in this healthy older adult population, this is quote unquote healthy, right? These are people that sometimes have memory complaints or complain about attentional issues. And so we feel like this is a population that may actually benefit from this type of treatment. And so one of our questions was, how long does it last? And another one of our questions is, can you get more gains by applying the stimulation multiple times, right? As I said, with the younger adults, we just did it over the course of an hour. And then we just sort of test them pre and post. With the older adult study, we made it a little different. We had them do the same protocol 3 days in a row to see if they would continually improve their multitasking performance. And then after the 3 days, we tested them 1 day later and then 1 month later. And as it turns out, the greatest gains occur after the first day. After the second day of stimulation, they're still improving, but less so. And the third day, even less, but they're still improving, right? And then 1 day later, those benefits that they've achieved are retained, maybe drop a little bit. It's pretty much retained. And then 1 month later, they're still better than the control group, although performance did drop a little bit. It's exciting to see that their performance was definitely better than the control group that received stimulation, but it was just a different frequency.
Huh. That's fascinating to me. Yeah, because I would say, so we do some of this in an uncontrolled, obviously it's not an experimental or a research environment. We do this, in our office, in our clinic, like you and I have talked about. And it is kind of unbelievable. Sometimes after the first stimulation session someone gets, it's like, oh my God, I've never had such a productive day. I've never, give me more of that kind of thing. And then almost universally, you don't see the same level of improvement. Like you're saying, it's incremental, but it's not like that sort of huge jump like you see from 0 to 1 after the first stimulation session.
Right. So one of our questions right now is, are they just adapting to the stimuli? Much like drugs where you can develop tolerance to it. So are they developing a tolerance to the stimulation? Or, and this is kind of the way my head is thinking about this, is I'm thinking that this 6 hertz stimulation may be just useful to help them really learn the paradigm, because in the end, there is a ceiling to how much you can like improve. Like there are physical limitations that people just have. Performance is not going to like this type of stimulation is going to make you superhuman.
It's not going to make anybody a NASCAR driver. Yeah, right.
Yeah, exactly. But it can help, hone your skills and optimize what you're given and what you have. And hopefully, maybe raise you up to where you used to be rather than where you are now. And so I'm starting to think that maybe they're just sort of getting their grounding, just really understanding how to play the game, how to engage with it. And it's just sort of facilitating the learning process, and I'm feeling like we're manipulating the learning curve, especially when we're doing this 6 hertz stimulation, because 6 hertz, yes, we've attributed to multitasking abilities, but others have shown 6 hertz frontal activity also has been associated with learning and memory. And so maybe we're just manipulating their ability to do the task more broadly. Maybe it really isn't specific to multitasking. So these are the things we really still need to tease apart. But what we really do like is one of the most exciting things that we saw from the aging research that we did was, aside from the fact that it's sustained for a month, maybe you've seen this in your own work, but there's a lot of individual variability. Not everyone responds the same to the treatment.
Yeah, for sure. And how do you make sense of that? Everybody's brain's different is a sort of oversimplification of it, but what are your thoughts on why people respond differently?
Yeah, so what we did to help account for some of that variability, because we knew in advance going into this study that there was going to be variability. And one of the hypotheses we had was that, look, everyone is getting the same frequency and the same intensity, so we're applying 6 hertz stimulation at 1 milliamp.
So that's an amount of current that they're getting, which is, not a huge amount. That's a, fairly low, medium dose.
Yeah, it feels a little tingly, but it's certainly not uncomfortable. Everyone on a side effects survey, everyone rated it a 1 out of a scale between 0 and 10, where 10 being the most painful, 0 meaning not noticeable. 1 is basically like, yeah, I kind of felt something. So it was really like highly tolerable, barely noticeable, but it had an effect. So that's great. But as I said, not everyone responded the same. And when you're applying this current to the scalp, we're assuming it's getting into the brain.
Yeah, it's a big assumption.
That's a dangerous assumption to make.
Big assumption. What you know is because there's 2 electrodes and you can measure the current passing across. So you know that from one side of the sort of, I call it the male balding pattern spot, that from the right to the left, and this is alternating current. So it's sort of like going back and forth, sending that stimulation. So there's not like a positive side charge and a negative side charge, and so you know that the charge is going from one electrode to the other, but you don't necessarily know the pathway that it's taking. We're not sure it's actually getting to the brain, so to speak.
Yeah, it could just as well go through the scalp, right? Because the skin is also a conductor, not a great conductor, but it's a conductor, and it could very well serve as that bridge so that the current goes in one electrode across the scalp, out the other electrode, then back in and back out, and left and right 6 times a second, never getting into the brain. Potentially, that's one possibility, right? And we know from a lot of other research that a lot of the current actually does follow that path. Fortunately, we can do modeling of current flow because we can estimate the conductivity and resistivity of the skin, the scalp, the cerebrospinal fluid, the gray matter, white matter in the brain, and we can model how much current gets into the brain. But in order to do that, we need to have an actual picture of each individual brain. Yeah. So before anyone got into this study, we brought them in for an MRI, and we got a really nice high resolution picture of their head, which includes the scalp, the skull, the brain, the CSF. And then, we use specialty software to sort of segment all these things and other software then to model it. And so you can assign resistances and to all the different tissue types and the CSF and such. And eventually you can see how much current theoretically got into each individual person's brain. And as it turns out, those people that got more current into their brain were the ones that had the largest response to the stimulation.
So that's sort of proof putting that the modeling software might be helpful. Because I know people have been after this for a while.
Yes, it helps validate that, and a lot of the animal work that's been done, basically that's already validated the models. But nonetheless, it's useful to know that the efficacy of stimulation can be affected by just your anatomy. And that is important to know, especially when you're dealing with aging populations or in people with neurodegenerative disorders, right? So as the brain degenerates.
So as the brain shrinks, so to speak, and the function of that.
Yeah. And so what fills up that space? Your brain isn't just sitting there in a void. It's filled up with cerebrospinal fluid, and that has a different conductivity, and that's going to cause the current to go in a lot of different directions. And so the more atrophied your brain might be, or more CSF you have, the smaller your brain, the less current is likely going to get into your brain. So people with, more atrophy, or, people with, say, AD, they likely would need a higher dose of stimulation just for the current to actually reach the brain. So you're applying a larger dose at the surface of the scalp, but the amount of stimulation that gets into the brain would be equivalent to someone else. You could double the dosage, but still see the same effects. You know what I mean? But here the variable was we kept the dosage constant, and the variable was, well, everyone had different levels of atrophy. And so there's different amounts of current that got into the brain. So that was one really interesting note that we thought was exciting to help understand the individual differences. The other thing was, how I said that 6 hertz was important because we previously showed that it was involved in multitasking? Well, that's the middle of the theta band. Theta is generally between like 4 and 7, 4 and 8 hertz, give or take. And not everyone shows a peak activity at 6 hertz. That just happened to be the average.
Right. Yeah. I was thinking about that when you said it.
Yeah. And so some people, they might have 5 hertz activity. Some might have 7. Some might have 4.
So when you said, let's just clarify what you said. So in other words, there's an accepted range. You mentioned at the beginning, delta, like this sort of slow, and typically when people are asleep or they have, something really wrong with their brain, typically if they're in a waking state, a concussion, it's something neurodegenerative tumor, etc. And then there's these other sort of ranges, right? It's like you could be in residential and be going really slow, like 10 mile an hour max. And then there's like 25 mile, but you could be going 23, 28 miles an hour, right? And so what do you mean that some people have 5 and some people have 7 hertz? What does that mean?
Well, just as you said, some people's brains just are faster than others. So when you're doing this multitasking paradigm, some people's brains are literally pulsing 6 times a second. Some people are pulsing at 7 times a second, or 7 hertz. And some people are slower. Some people are down in the, 4 hertz, 4 pulses per second range. And as far as we know, we haven't seen that definitively means that they have something wrong with them. It's just, that's like your fingerprint, if nothing else, as far as I know. We haven't really dove very deeply yet into the meaning of this, decrease. I know in other frequency bands, well, I don't want to get too far off track, but I know in healthy young adults, we generally, if you just relax, record your EEG and look at, the different frequencies that are naturally observable. Yeah. There's always this spike. Well, not always, but usually there's this spike right around what we call alpha. And that's usually around 10 hertz. That's sort of like this natural, really dominant peak in what we call
the old peak alpha, posterior dominant frequency. Okay.
Yeah. And as you get older, that peak alpha actually gets lower and lower. So as you get older, it might be 9 hertz or maybe even down to 8 hertz. It's been associated with aging. It's also been associated with other, neurodegenerative or psychiatric issues as well. And so the utility of peak oscillations is still an area of investigation. I wouldn't say that it's a great biomarker at this point, but it's an interesting note that there is this variability between people. It may have something to do with brain function, or it just might be an epiphenomena that, it's just a coincidence that just people are different and that's just how it is. So at least in the theta band, what we're seeing in this, 4 to 8 hertz region, not everyone had a peak at 6 hertz. And yet here we are stimulating at 6 hertz. And so what we saw was, because we recorded EEG while they were doing these tasks, we saw that the people who benefited most from the 6 hertz stimulation were the ones who indeed had 6 hertz oscillations coming from their brain. They're the ones that needed it. They're the ones that got it. Other people who are, using 4 hertz, whose brain was oscillating at 4 hertz during this task, they didn't really benefit from 6 hertz stimulation. It's like the frequency was off. We missed the mark. And that's why people believe in that, this backs up a lot of research from in vivo and in vitro work in animals and such, basically indicating that the way this transcranial alternating current stimulation, this TACS, the way this stuff works really seems to happen through entrainment and resonance, meaning that you need to really stimulate at the frequency in which your brain is trying to oscillate. So if your brain is trying to burst at 6 hertz, if it's trying to oscillate at this frequency, you need to match that frequency.
But let me ask a clarification question. So what I'm understanding from you so far is that there are challenges in essentially personalizing this. You can't necessarily, like in a study, oftentimes we'll say, okay, we're going to arbitrarily say, give this amount of stimulation at this speed. We're going to give this power at this speed, at this hertz frequency. But because of individual variation, let's say somebody's Alzheimer's, somebody's just different, somebody's, like 20% of people just happen to have a slower frequency or something like that. An ideal situation might be to say, as opposed to say, hey, we're going to give everybody 6 hertz, we're going to match whatever their brain is doing. And then also sort of do an MRI ahead of time, figure out how much current. We have to ramp the current higher because this person has, like, let's say Alzheimer's, and they have more fluid in their brain.
Yeah. That's like an ideal scenario. But of course, MRIs are expensive. EEGs are, time consuming. Well, MRIs are time consuming too, but it's not always optimal for everyone to do these things. And so one way that people have suggested to sort of get around this is just by applying a higher stimulation intensity, right? So just sort of play it safe. Oh, you know what? Instead of 1 milliamp, let's just go up to 2, because that will ensure more current will get into the brain. And in terms of the frequency, it's interesting that others have shown that even if you don't perfectly match the frequency, if you get close, a higher intensity will almost act like a magnet and sort of
pick it up.
Yeah, exactly. It'll help entrain the brain. So if you're oscillating at 5 hertz and you apply a 6 hertz stimulation, it may do nothing at a low intensity, but then you increase the intensity, all of a sudden, now all of a sudden the 5 hertz will sort of move into the 6 hertz, and you'll be able to sort of entrain the brain that way. I mean, honestly, you could take this, to ridiculous intensities, and eventually, as we know from electroconvulsive therapy, which is about 1,000 times stronger than what we're doing, but still a technique that's used today to treat depression. So let's not pretend like this doesn't still exist. It does, but it's 1,000 times stronger, and that induces a seizure. But a seizure is essentially you just induced currents that are strong enough to basically entrain everything. And a seizure is essentially a whole huge swaths of the brain just firing synchronously.
Seizing up.
Yeah, exactly.
Well, okay. So that was really interesting. So that's on the theta, so that we talk about theta, which is sort of a slower brain speed or oscillation, like you said, neuro-oscillations. So one of the things in the Alzheimer's world, and I get this, there's in Forbes or in Time, like usually there's been several sort of pieces out of a variety of institutions, most notably MIT's lab, talking about gamma stimulation. So a faster speed. And I know that you've been involved in using gamma stimulation. Can you kind of give us kind of the story of first, what is gamma and what is gamma stimulation? And then your work and what your observations have been so far with.
Yeah. So, as we've been talking about these, we give different frequency bands. A band means like 1 to 4 hertz, and we give it a name. We call it delta. When I say theta, I'm referring 4 to 7, 4 to 8 hertz. Gamma is a higher frequency. It's usually 30 to 50, 30 to 70, depending on who you talk to. And so it's these higher frequencies. And as you had mentioned, this lab out of MIT, Dr. Liwei Tsai, her work has shown that you can apply oscillatory stimulation, whether it's through optogenetics, meaning, essentially shining a light within the brain without getting too technical, or just shining a light to the eyes, like flickering a light at 40 hertz or strobing sound at 40 hertz. And by doing that, she's done this in animal models of Alzheimer's disease and shown that it can help improve biometrics that are associated with Alzheimer's disease, as well as improve cognitive functions such as memory, long-term memory function.
So less of the buildup of some of the bad stuff that we see typically in Alzheimer's, and actually some improvement in function and brain function.
Yeah, exactly. So what's known as beta amyloid is the necessary but not sufficient biomarker associated with Alzheimer's disease, right? And these amyloid plaques build up over time, and you can reduce that amyloid load through this gamma stimulation. I am, well, with my colleague, I don't really do animal research anymore, but my colleague at UC Davis, Min Zhao, we worked together on this project trying to emulate their work, but instead of flickering lights, we decided to apply electrical stimulation at 40 hertz. And then we assessed dosing, because some of the most fundamental question is how strong of an intensity do we need? We tried a few different intensities, and not terribly surprising, the higher intensities were more efficacious than the lower intensities. But even still, even at the lower intensities, we saw improvements in memory, as well as improvements in these biomarkers that are associated with the development of Alzheimer's disease, specifically lowered beta amyloid load. And we saw increased microglia proliferation. And microglia are these neurons, these cells that help clear the amyloid plaques. And so it's not terribly surprising then that we see lower amyloid load, because it's got to go somewhere. How did it disappear? Well, it turns out that we believe what happened is that we helped increase the microglia activity, and that helped lower the amyloid load. And, I don't know if there's a causal effect here, but in doing so, somehow we also improved episodic memory, just as, Dr. Tsai's lab had shown, and some other groups as well. And so it's really exciting that multiple groups around the world really have now seen this effect in animals, and is now starting to transition into human trials. And there have been a few small trials to date showing efficacy of this gamma stimulation. And in fact, we just finished our sort of pilot study, also, demonstrating the efficacy of 40 hertz stimulation.
So can we break this down? So I get the chills, I'm super excited to hear what you're saying. I think this is a doable thing. Like, this is not pie in the sky. This is like something that's being worked out. There's a practicality to this that's maybe people don't realize.
Yeah. And in terms of practicality, I don't think people realize, I certainly didn't realize how cheap these things are. You buy a research grade neurostimulation device, they're pretty expensive. But honestly, if you look at the schematics of it, you can build these things for really cheap. We're talking like $10-$20. Like if Radio Shack still existed, that's essentially like you could literally walk down to your local Radio Shack and buy them all the parts you need for like $20 or something. You just need some skill in soldering and such. But obviously, I'm not going to tell people to do that, because you really do need to control the currents and do it in a better environment. And obviously, these things are still in research phase, right? So I do not want to promote people running down to their local, electronics shop and starting to hack together TACS devices. But nonetheless, the point is, it's practical. Once these things become, right, it's still under research, but if they do demonstrate efficacy and they prove to be a nice, useful therapeutic, likely in conjunction with other treatments, but nonetheless, if it does come to market as a viable treatment for AD, Alzheimer's disease, these devices should not be expensive, and they're very portable, they're easy to implement, and they're highly tolerated. They're well tolerated. So it's really exciting about just taking a step back from the science and just say the practical applications of these things, the idea that these things could scale and be implemented easily, to all corners of the world, I think is really exciting for me. That's essentially why I'm particularly interested in TACS as opposed to other types of neurostimulation, which do require really expensive and complicated electronics like TMS or ultrasound and things like that.
So can we maybe draw another sort of bright circle around that here? So with human beings, how did you, where did you put things, and why did you choose where you put the electrodes and things like that?
Yeah. So right now, there's so few trials in humans right now, you can't really guide anything based on what other people have done to show efficacy, right? And the human brain, the anatomy, just the way everything is laid out is so much different than the animal models that have shown efficacy to date. So you can't just say, oh, just put the electrodes right here because it worked in these mice. It's like, well, no, that's also not going to work well. So what we decided to do was, we knew that we wanted to target hippocampal regions, which is generally, out of reach for the type of stimulation we're doing, but some current does get in there, and if you position the electrodes correctly. So we did a bunch of modeling of a bunch of different configurations to try and optimize the stimulation so that I would reach not just the hippocampus, but other regions that are part of an episodic memory network. And what that means is that episodic memory is essentially what people oftentimes would refer to as just sort of long-term memory in a hand-wavy manner. But basically, that's what's most affected in Alzheimer's disease, is this sort of episodic memory network. And that's what people complain about when they have AD, is that, oh, my memory, oftentimes when you're dealing with memory issues, it's because of, dysfunctional hippocampal regions, as well as regions in sort of the inferior frontal cortex, as well as parietal lobe. So it's sort of like the frontal region instead of the back. And so we wanted to target these regions because we knew that they're in a network together. And what's important with this brain stimulation is that if you can stimulate just part of a network, others have demonstrated, and actually we have some evidence of this as well in-house, is that if you stimulate sort of a node of a network, regions that are functionally connected, you manipulate that activity, it'll reverberate throughout the network. So even if our stimulation can't quite reach the hippocampus, if we can hit a region of the cortex that's communicating with the hippocampus, then we believe we can affect activity there as well. But nonetheless, we did a bunch of different modeling just to try to place the electrodes in such a manner that we believe it would hit multiple nodes of an episodic memory network. And then we just...
You guys are like lobbyists for the brain. It's like you find the most influential member of a congressional
exactly.
subcommittee, and you say, okay, that's the gal. We got to pay her, right? Okay. So where did you put the money? Where did you place the electrodes?
Well, we went big. We went 8 electrodes, 4 on each side, spanning frontal lobe all the way to parietal. So if you're familiar with EEG electrode coordinates, our frontal ones would be close to the temple, sort of, I believe it was, don't quote me on this, but largely around F7, F8, close to the temples. And then we just moved back. So we had a pair at F7, F8, a pair at, I believe, FT7, FT8, then T7, T8, and then I believe P7, P8, somewhere around there. It basically, sort of lateralized just above the ears, going from the temple over the ear, and then, sort of to the back of the head.
And each one of these is its own. Each one of these is sort of its own unit, right? Like,
yes,
it's 4 TACS units running. Basically.
Well, it's all actually the TACS device that we were using has upwards of 32 electrodes, I think we could choose from. So we chose 8 and stimulated from 8 simultaneously with the same device. And it passed current left to right. So all 4 electrodes were simultaneously stimulating at the same time, passing from the right to the left, then back from the left to the right, left, right, at 40 times a second, 40 hertz.
Beautiful. Was it a Soderix machine you're using? What do you use?
This one, actually, we just did a StarStim 8 channel. It was just StarStim 8. We didn't record EEG in this one, unfortunately. But we did get a lot of really interesting other metrics. We got MRIs, resting state functional MRIs, so we could see, how the brain is sort of connected functionally as well as anatomically. So we got DTI, which is sort of like the ability it enables us to look at how the brain is anatomically connected. And then we got resting state activity, so we can see how the brain functionally communicates to each other, like within its own networks. And then we also got magnetic resonance MRS, magnetic resonance spectroscopy. So we're looking at the excitability. So it basically can give us estimates of neurotransmitter densities and other metabolites.
Glutamate, GABA, things like that. Okay.
Yeah.
What are you pulling out of that so far? Because actually the glutamate stuff is very interesting to me.
The results that we have so far, and again, we're literally writing this manuscript as we speak. So I don't want to get too far ahead of myself, but I can tell you that the result that we're confident in is that we were able to at least improve episodic memory, multiple indices of episodic memory.
Do you know how long it lasted for? Again, same kind of question.
We do not know, unfortunately. We did this over the course of a month, and just to see if we could move these measures, because this was a population that is, has mild cognitive impairment. That's sort of a pre-dementia stage where they're at a raised risk of transitioning to dementia. And so unfortunately, we didn't get follow-ups yet. We're planning on, follow-up studies. We just wanted to do just a feasibility and like initial efficacy. There's no point in getting follow-ups if it doesn't work, right? So we were kind of, hedging our bets. Let's just look to see if it's tolerable, feasible. Is there any signal that we're actually doing the right thing? This is why science takes forever. You do a study and say, yeah, this works. Now let's answer the next question. The next question is, does it last? Also, we did this, and there's a huge caveat right here. We did this in a single arm design. I mean, generally, the measures that we were looking at, they don't improve, right? They generally do not improve in this population. So the fact that they did improve is really amazing to us. But we did not have a control group. So huge caveat, big asterisk.
Yeah, okay, we get it. Big asterisk, we get it. I totally understand. We'll tune in for more.
Yeah, exactly. But others have controlled trials, and others have shown that it works in terms of memory. And so what we're really trying to add here is the fact that this configuration works. It works with this, electrical stimulation, not just light or sound, and that it actually can move some of our biometrics. And so we're still waiting on the blood work to see if amyloid was lowered, other biomarkers that associated with AD progression. So we're looking at tau, neurofilament light, neurogranulin.
What else was you said tau and neurofilament light chain, anything else?
Yeah, we're waiting on all these other biomarkers yet. So we'll see. We'll see.
1.6?
Because we were able to improve memory, we feel like just by virtue of the fact that we were able to improve memory, I feel like requires a follow-up study just to see, let's control it. Let's get a control group. Let's see how long it might last, and then hopefully replicate our own findings, right? So
you mentioned, the areas, and, without getting too technical, you mentioned, so the inferior frontal gyrus and interparietal sulcus, to sort of get at the network of memory that's often affected in mild cognitive impairment that at least is likely to lead to the Alzheimer's. Of course, there's different kinds of, as you well know, different kinds of mild cognitive impairment. Did you check to see beforehand that the folks that you included in your study had the kind of memory problems that was most likely kind of Alzheimer's?
Yeah, so you're right. There are many different subtypes of MCI and mild cognitive impairment, and so we recruited specifically the amnestic subtype. So those that did have memory issues. You're right. Otherwise, what's the point? What are we trying to improve here? Yeah, no, you're right.
And then the model that you used, sort of like, I don't know, near the resources or the experience you do in terms of sort of network neuroscience. As humble as you are, Ted, I mean, you have a nice track record here. And let's say in this particular study, where did you call from that I can cite a couple of papers, even just from the last several years, go back to 2013, I'm aware of, but how did you say, okay, we're really certain that these are the areas that we want to charge, that we want to stimulate so we can get into that hippocampal area? And I'll add to that question, when we do MRIs in some of our folks, just, clinically, because they've not had them done, and we can get a volumetrics, and we can sort of have some software that will measure how big or small that memory center, that sort of hippocampus is. Some of these people have shrunken hippocampuses that are less than the first percentile, meaning they may not, I don't even know if they're there. So what are we stimulating? You know what I'm saying? I don't know if you looked at that. I'm sure it sounds like you have the technology. You definitely were able to look at that.
Yeah. So one nice thing about TACS, this electrical stimulation, is that it's a blessing and a curse. It's not very precise. When you're dealing with other, neurostimulation, neuromodulation techniques, you have the error bars on the order of millimeters, right? Maybe a centimeter. With TACS, this electrical current goes everywhere. It's actually hard to be precise. So the fact that we say, oh yeah, we want to target this specific subregion of the inferior frontal gyrus, it's like any decent reviewer is going to scoff at us and say, yeah, you hit the frontal lobe, you hit the parietal lobe, you hit this quadrant, basically. We're basically bathing the brain in this stimulation. And that's essentially what a lot of the animal studies did as well. When we did our study at UC Davis, where we were doing gamma stimulation in a mouse model, I mean, we used the tiniest little electrodes we could find, but the mouse brain is tiny. When you model the current flow in the mouse brain, it really hit a significant swath of cortex there. It's really, really, bathing the brain in these electrical fields. And mind you, these electrical fields are weak. They're not strong enough to cause neurons to fire, which is why we think it's important to use frequencies that the brain is already trying to oscillate at. And they're apparently something which is unclear why, but apparently 40 hertz is an important frequency of oscillatory activity.
So that was my next question. Why 40? Why?
It's one of those things where someone found it to work and everyone's following up on it. And future research will likely assess why that frequency. But right now we're at such an early stage. Everyone is focused on the utility of it. Is it actually a reasonable therapeutic? Because there are people who need therapies. So the way the science is working right now is, let's just see if there's something here that could be a great therapeutic. And if it is, then we can kind of work backwards to understand the why. You know what I mean?
Well, there's a lot of medications that have, as you probably know, there's a lot of medications that have been approved. And, as long as the safety profile is reasonable, it works. Even sometimes we don't understand it. It just was like, oh, somebody saw it as a side effect in another study. And let's try it for that. And we're not 100% sure why it works.
Yeah. 40 hertz pops up. At least I've seen 40 hertz. And then I'm coming from a very specific field. So maybe my blinders are on, but whenever I see 40 hertz, it's usually associated with like perceptual processing and things like that. This gamma frequency is oftentimes associated with sort of local computations, and so maybe there's just something fundamental about that frequency. But I'm not sure why 40 and not like 80, not 120. It's, again, great questions for future research, but that research may never get done if this whole thing falls apart and turns out it didn't really work. It kind of works, but it really isn't that great. And then we never know. But as of right now, where we stand, it seems to be a very reasonable approach and certainly worthy of additional research.
Yeah. So good luck. I'm very excited to sort of follow up with you so that you guys are seeing.
Yeah, we are too. We're keeping our fingers crossed, because in the end, we're just trying to help people.
You mentioned, and I kind of followed up on it, there's a Robin Carhart Harris, who's really a well-known name in the world of sort of, I would call it real neuroscience, sort of hardcore neuroscience in psychedelics and the use of psychedelics and trying to understand what impact it's having on, at least at a systems level, for the brain, cognition, and then what impact does it have to improve people's lives. But he's, he was just recruited to UCSF, to Neuroscape, and that sort of the similar division or location.
Yep, we're all in the same center now, and it's great. It's fantastic. He's a great colleague. He's really sharp. He's doing amazing research, as you said, both at sort of like the basic fundamental science side to understand the mechanisms, but also on the clinical side, the translational side, where he's trying to assess the utility of these drugs to help people with things like depression, treatment-resistant depression, mind you. So, talk about shooting for the fences right at the bat. You could just try to see how well it works in like other, depressed populations where it may just be more effective than perhaps some of the other current treatments. But really, he's just going straight for all right, nothing has worked for these people. They're still depressed. All right, let's try psychedelics.
Well, you and I both have known people that are severely depressed, and that's an urgent problem, and it continues to be. It doesn't seem like it's getting better in recent years.
Yeah, unfortunately, I can't speak to his research, but from the data that I've seen to date from his and others, it's really encouraging, and so we're really excited about it. Excited to have him, working with us and around us.
My question for you, though, is there has been some sprinkling of data around, and there was some entrepreneur that was, again, in publishing things in magazines, a couple of articles on and I've had a couple of patients ask me about this, which is the use of psychedelics, whether that's sort of psychoactive mushrooms like psilocybin or something like more synthetic like LSD, that it may sort of spark something regenerative, something. You think that you said you may be including that in one of your kind of future projects. Can you kind of speak about the thinking and what maybe the hypothesis is there?
Well, I'm not sure how far along any of this. I don't have any projects in the pipeline right now in terms of trying to spark neuroplasticity. I know Robin has a bunch of this going on, so I can't really speak to what he's up to, but I can see how others have shown that, these psychedelics can spawn or sort of jumpstart neuroplasticity, the idea that it helps the brain sort of restructure itself. And that's why, people believe that these drugs are potentially very useful for therapy when done correctly in a controlled environment. And so, it's exciting, the fact that it can spark neuroplasticity. And that's why, it's not just being assessed in psychiatric populations, but also there's at least one trial that I know of, I believe at Johns Hopkins, that's assessing whether psychedelics may be used to help stave off depression within an AD population in people with mild to moderate, I think, Alzheimer's disease. Sorry, I can't really speak to their inclusion criteria, but I did come across one of their studies. I'm like, oh, cool. It's good to see, because I knew that, I saw an article saying that, oh yeah, people should, at least because of the potential for neuroplasticity and because Alzheimer's disease is a neurodegenerative disorder, maybe there's a way for psychedelics to improve, plasticity, and maybe there's a way for it to help, probably not reverse course, but at least maybe help maintain for a little while. Who knows? But it's at least worth looking into. And it sounds like at least this group at JHU is trying to assess the effects on depression, which already has, grounding, like we already know that there is at least some indicators that it may be useful in depression. So it's interesting that they're trying it in depression with people that have AD. So hopefully this will be a generative study, like meaning that it will give us new insight into the efficacy into a population that has a neurodegenerative disorder. So I'm really excited to see what comes of that. And yeah, maybe somewhere down the line, I'll get into that arena. But as of right now, I don't have any psychedelic studies planned. I know Robin does. He has, he has a whole laundry list of studies. Although I am sort of tangentially working kind of in that realm, because one of my questions is, when someone's going through these psychedelic therapies, there oftentimes will come a time when they really can't speak or express what they're feeling. And so it would be great if we could decode their emotional states using things like EEG or other, sensors. And so one of the studies that I'm, running right now is in healthy adults that are not under the influence, but just helping create methods to detect emotional states in real time. And so if that's successful, then in theory, down the road, then we'll try to implement that in the population where they're undergoing a psychedelic treatment. Likely to start with a healthy population undergoing psychedelics, just to see if we can decode their sort of mental state. But that would be the idea, is that the end product would be that if we could use these tools to help enhance the treatment in a meaningful way, because we don't really know what's going on during the treatment. All we know is that it seems to work, but is there a better way to do it? So these are just some basic questions, but they're all very just sort of like hand wavy ideas. But the project I'm doing right now is not hand wavy. We are actually still trying to decode emotional states using more sensors than I think anyone has ever used before simultaneously.
Wow. Okay. Anything that we didn't talk about that maybe seems relevant to sort of mild cognitive impairment and potential Alzheimer's in the realm of sort of music and entrainment?
Yeah. I mean, that's sort of my whole other, if we had another hour, but yeah, I'm actually writing up a study right now demonstrating efficacy of musical instruction in older adult non-musicians, showing that just with 2 weeks of training, you can improve, well, not just timing abilities, but attention and memory abilities. And that's really exciting. And we, show the changes that occur in the brain, and we're really excited.
What did you do with these folks?
So what they did was rhythm training on a tablet. So they played essentially a video game that we developed in-house that helped them sort of entrain to the music, so to tap rhythmic patterns. And by tapping these patterns, every time they touch the screen, it creates like a bongo noise. And so they're trying to tap to the beat, but there are these little cues on the screen, kind of like Rock Band or Guitar Hero. You know how these things kind of come at you, and then there's like a little bar and that tells you sort of when to tap. It was kind of like that, a little different, but basically what we did was had these older adults play either the rhythm training game or a word search game as like a control group. And just the rhythm training game showed improvements in sort of attention, specific attention for time. So really like their timing abilities. And we also saw an improvement in short-term memory performance. So they were able to improve their ability to recall faces, which has nothing to do with the music task at all, which is what's most exciting about it. And other people have shown that, yeah, musicians compared to non-musicians can show improvements in memory and attention abilities. But here we're able to show sort of like the very beginnings of it, in that just 2 months, you start to see these changes. And with more training, with years and years and decades of training, others have demonstrated that, a musician, those years of training does seem to have some sort of protective effect long-term on their cognitive ability, and it lowers their risk for progression to mild cognitive impairment and Alzheimer's disease.
Yeah, that's awesome. I told Dr. Ben Hanstead, who's a researcher like University of Michigan. Again, he was on the show a few months ago. and he had a couple of questions and he wanted me to toss up to you, which I know are going to be doozies. So maybe the answer will be, I don't know, but it's a good question, but let me toss about you, okay? This is for you, Ben. The question is, when talking about alternating current stimulation, so the entrainment, so does the sort of stimulation need to occur online to yield benefits? And what might those benefits be? Or do you find the benefits persisting offline, and for how long after? I think some of that's been evident from our conversation, but if you could address that directly.
Yeah. But I'm happy to reiterate, my experiences and what I've read in the literature is that, and I've even seen offline effects. So I think up to this point, I've been saying, we've been doing stimulation while they're engaged in a task, but you can get, depending on the stimulation and what you're trying to move, what you're trying to target, you can get offline effects. But in general, it's my opinion that online effects seem more robust, and largely because, especially with alternating current, you're trying to target a frequency in the brain. As I said, these currents aren't strong enough to cause the brain to oscillate at these frequencies. They're trying to boost the frequencies that are already there, or the frequencies that are trying to help underpin some cognitive function. In our case, it was multitasking in 6 hertz, brain activity. So if someone's going to sit on a couch and just like stare out the window or just stare at a TV and then apply 6 hertz stimulation to themselves, I don't think that's going to really like do a whole lot for them. It's kind of like, shoot, it's not that I take steroids, but like, it's my understanding that if you're to take steroids, you're going to get stronger if you exercise. You don't just take it and sit on the couch. This is something that's going to help you in the task that you're trying to do. So I think online is really more efficacious, largely because you're trying to match the stimuli with an activity that is supposed to evoke the frequency of brain activity that you're trying to target.
Yeah, I'm definitely in that camp as well, for sure. And then the question of does it persist offline?
Right. And so I believe it persists offline, not necessarily because the frequency is still ringing in the brain or something like that. I believe what happens is that as you boost this brain activity, your brain adapts and it learns. And that is essentially what I believe is happening here. And that's why, in my mind, we're seeing, improvements a month later. These older adults, they did 3 days of stimulation, but they show that their performance improved to such an extent that those improvements were maintained a month later. They differentiated from a control group. It doesn't mean that you stimulate your brain once and that it just sticks with you like some drug that's lingering in your system. Not at all. It's really neuroplasticity, right? You're changing your brain in such a way that it makes you perform at a higher level. And once you've learned it, it sticks with you. Yes, memory fades over time, but these are neuroplastic changes and they will stick with you for at least a month or so. Although to be fair, as I started off talking about that NeuroRacer study, where they showed that a month of training can improve multitask performance. What I didn't mention is that they tested those people 6 months later and 6 years later. And those improvements were still there, which is crazy. 6 years later. But, it's kind of like they say, you never forget how to ride a bike, right? So the 6 years later, I don't think the transfer was still there, right? So the benefits in other tasks, that had faded away. But what they had trained on, right, that stayed with them.
So that's super interesting to me. Well, so just a little follow-up that I really just thought of now. So because there is a little bit of a tail effect, like from the sort of neurochemistry that I'm familiar with, at least, there's an effect while someone's wearing these, like the device, or you have the electrodes on you. And that's where the kind of the most effect is. But then there's like a trail, for a couple hours, sort of a sub or a post-acute effect. Do you have any idea if the window, let's call it a neuroplasticity window, or a chance for the brain to change and learn? Is there anything in sort of your knowledge that okay, first you do the stim and then you do something else afterwards? Or does that seem plausible?
Yeah. No, that's a really, really good question. I wish I could tell you the definite answer. I think it makes sense. I think intuitively, it seems like something worth investigating, but I don't know whether that means it's a specific best opportunity. So the way this stimulation works is that it does have sort of a ramp up and, as you said, a ramp down effect, right? And if you were to apply stimulation for 3 minutes, maybe even 5 minutes, it might not even do anything. It takes a while for these effects to really start building up. And so when we apply stimulation, it's, at least 10, 12, 20, 30 minutes we'll apply the stimulation. And then we're starting to see real effects, and they sustain for a day later. Perhaps we would see greater effects if we had stimulated them for 30 minutes and let them train for another 20, 30 minutes, right? That's a great question. We haven't tried to control for that. And I'm trying to remember. Yeah, off the top of my head, I can't think of a study that specifically titrated. I'm pretty sure it may exist in the TDCS literature, but I don't know about it in the...
So he's also curious whether altering a given frequency, so changing, the speed, so to speak, for, so let's say to get and train in one task, to get one cognitive kind of a benefit, let's say memory versus being able to, multitask is probably not a great example, but to remember faces versus to be able to do something faster. If you're trying to train one thing, does that kind of come at the expense of other cognitive functions? Like if you're trying to get to one thing, do you see that another thing suffers in it? So how might you balance that?
Yeah. So there was a paper that came out years ago. It's called The Cost of Cognitive Enhancement, I believe, by Roy Cohen-Kadosh, who used TDCS, right? So there you have an electrode that serves as an anode where the current goes in, and they have a cathode where the current goes out. And it's generally thought that under the anode, you sort of make the brain a little more excitable, and under the cathode, it's a little more inhibited. And what they demonstrated was there was a cost. So under the anode, those cognitive functions were enhanced, but under the cathode, those cognitive functions were suppressed. With TACS, the current is sort of oscillating back and forth. So there really isn't an anode and a cathode because they keep flipping polarity. So is there a cost associated with TACS? I have not seen it. I haven't seen anyone publish or even anecdotally speak of some sort of cost. But, my intuition is really like anything you do comes at a cost. What we're doing right now is sitting at a desk, talking to each other, and that comes at the cost of being sedentary. So we're no longer being active. So our hearts and our bodies are literally decaying as we speak, very, very slowly, subtly.
Except our minds are being stimulated, presumably. His mind is, maybe yours is.
Our minds are being stimulated, but our brains will only work as well as the energy that is fed to it. And that energy comes from our heart, the blood, the oxygen that is being carried against gravity upwards into up our neck. And so if we're not...
food we eat, oxygenation, our nutrients, all the good stuff. Okay.
Yeah. So
you're making a good case for a multi-domain study, where we do all this stuff.
Yeah. So to answer your question, I haven't seen any cost with TACS associated with it, but you're right. It's a really interesting idea that perhaps you stimulate at 6 hertz and then you just sort of bias your brain more towards that and less towards other frequencies. But to be fair, I haven't seen it. We've tested other transfer metrics, and either it doesn't transfer or it transfers and it gets better. I've never seen a negative transfer.
Yeah, some got worse and other things.
That sort of speaks to the question, but I wouldn't call it conclusive because there's just so many different possible forms of transfer. And usually people design studies to assess what might improve, not what might be negatively affected.
So either we don't know, but what you've seen so far, just to again summarize some of the technical pieces for the listeners, it sounds like when we're studying, we're looking at a particular endpoint. Those things will often improve. It doesn't seem to come at the expense of something else. It might not improve other things, but it may not sort of work in other areas, but it doesn't seem yet to be obvious that it makes other areas worse. However, we're not always looking for those things. So.
Exactly. And to be fair, not improving other things is a bit of a cost, right? Because you could be doing other things, that might improve. Because, as they say, if exercise were a pill, everyone would be taking it. And that does improve multiple cognitive functions, mood, sleep, so, there's always a cost.
Dr. Zanto, thanks so much for taking the time, and your work in general. It's a pleasure and honor to speak with you.
Oh, thank you. I appreciate that. I had a lot of fun anytime.
So that's our episode. I hope it was useful to you. Check out the show notes on iTunes or on our website where we've summarized the key points. If you find the information here valuable, please consider giving us a 5-star rating on iTunes and leaving comments in the comments section. It will really help us bring this message to as many people as we can. If you have questions or comments, connect with us on social media. Finally, to support us, go to patreon.com/evolvingpast and consider hitting the button and becoming a patron of this show. That's Patreon, Patreon, patreon.com/evolvingpast. Thanks, and talk to you next time.